Hi, I'm Will Taylor.
And I'm James Tuhiwai, and our honours project was a Lake Fryxell profiler.
Our task was to design an underwater sediment profiler for our client and supervisor, Professor Ian Hawes. Underwater sediment profilers are used all over the world, from measuring CO2 levels in tropical reefs to monitoring lake health here in New Zealand. The profilers are deployed in place by divers and controlled via hardwire connection, while some very expensive models can be operated independently for short periods of time. Professor Ian Hawes, an Antarctic researcher from the University of Waikato, is wanting to research the microbial mat, which sits at the bottom of the frozen lake, Lake Fryxell. For this purpose, Professor Hawes is wanting to deploy an underwater sediment profiler to sit in the Lake Fryxell environment, taking a series of measurements every hour while operating completely independently for 12 months.
Development. The current profiler was produced and designed by Unisense, a marine research and technology development team located in Denmark. Using principles from the current design, some of the features were incorporated to create something completely new, which would assist in developing a more durable, lightweight, and reliable and efficient design. Frame design. The frame was designed around a centralized base plate with a 3 tri-legged orientation. Most of the frame and supports are made from aluminium 6061. It's lightweight, weighing approximately 11 kilograms in total. The mechanism is also located in the center of the design, and this will allow for easy setup and usability for divers when deploying in Lake Fryxell. The design is smaller and more compact than the current model to assist with travel requirements. Watertight design. From the model as shown on screen, we have the static and the dynamic watertight. Both the static and the dynamic watertight are made out of acrylic. The static watertight is based on the top of the design. The dynamic watertight is on the bottom of the design. The static watertight is suitable for up to depths of 300 meters, and it also houses most of the electrical components which control the drive system, and that's the stepper motor just located below. The dynamic watertight, this one below, has a sealed bearing which allows movement to be transferred through the lead screw to the stepper motor while also protecting the housing from water exposure.
This is our electrical prototype. For the profiler to work, it needs to calibrate itself to the height of the microbial mat. An Arduino controls the step motor to lower the probe down toward the microbial mat. The probe will recognize a sudden decrease in oxygen levels. It's at this point that we know that the probe has touched down on the microbial mat. We didn't have the probe or the microbial mat, so we had to use a reed switch with magnets to tell the profiler when we wanted it to stop. So as you saw, it was just calibrated then. Once the profiler is calibrated, it will then begin its routine testing, where every hour the profile will take 24 sets of measurements at different heights. It will save these measurements to an SD card using a Raspberry Pi, so that the data can be retrieved at the end of the deployment. From testing the profiler's total power draw while running and sitting idle, we found that the profiler would need two 2,688 watt-hour lithium iron phosphate batteries in order to operate for the full 12-month period. Our profiler is only a prototype at this stage, the first of many iterations to come. We estimate a total cost of $24,000, which is significantly cheaper than alternative profilers, which can cost around $100,000. But we can see that the innovations that we have made will not only be useful for Professor Hawes' research. A cheap, isolated profiler that is suitable for long-term deployment will fill a current gap in underwater sediment profiling technology, opening doors for more research to come all over the world.
I would just like to thank our supervisors, Dr. Rachael, Dr. Harish, Devaraj, and Professor Ian Hawes for the support through the project and guidance towards completing our design.